So this is 20.4.3, the period of an oscillating spring. And we're solving problems involving the period of a mass oscillating on a spring. So yesterday when I had that mass hanging from the ceiling and I put a spring in between it and the string and we got it into oscillation, there's a connection between the period of oscillation and the spring constant. We also saw yesterday, and this would normally be what I would do here. I mean, I guess I can do it again. I'm not going to take up too much time here. But if I take a look at this spring, and I hang a 1 kilogram mass from it, and we determine the period of oscillation, which is the time from the top back to the top, or from the bottom back to the bottom. That will be a different period of oscillation than if I hang this on it. The period of oscillation here is quite small. So the larger the mass, the larger the period of oscillation. I don't have extra springs here because that's going to be part of your lab tomorrow, but if I hang a spring in this situation that has a smaller spring constant, I think you would expect that it would take longer for the mass to go up and down because the spring is more loose. It's not as rigid. And it turns out there's a formula. So this is the lesson. This is the new material. This formula, which is on your formula sheet, can you take a look on your formula sheet to see where it is? I believe, even though it doesn't have anything directly connected with waves, I think you're going to find it under waves. And this says that the period of oscillation is equal to 2 pi times the square root of the mass over the spring constant. That's it. That's the new material. We're going to do 2 or 3 examples of this, and then we're going to talk about the formula that you can use for a pendulum. Okay? So determine the frequency of vibration of a 500 gram mass on a spring with a spring constant of 28 newtons per meter. Well, we don't have a formula for the frequency, but we do have a formula for the period. And we also have a formula relating the frequency to the period. So once I find the period, I can just take the reciprocal of it and get the frequency. The period will be equal to 2 pi times the square root of 0.5 over 28. And once again, particularly for a new formula that's like this one that has square roots, I'm really not concerned about the units. The units work themselves out. And in Physics 30, we worry more about that. So you need to take your calculator and figure out what this is going to be equal to. Two times pi times the square root of the mass, which is 0.5. It's 0.5 because 500 grams divided by 1,000 grams per kilogram gives you that, over the 28, and I get 0.84 seconds. Anybody else in agreement? Okay. What is the frequency then? Well, the frequency will be the reciprocal of that. We're dividing by 1 by second, so that's going to give us units of per second, which is hertz. It'll be a little over 1. So it's about 1.2 hertz. So it takes 0.84 seconds to oscillate up and down once, and the frequency is approximately 1.2 hertz, which means it goes through 1.2 complete oscillations every 1 second. Pretty basic question. Let's take a look at number 2. What if I give you that 500 gram mass and I give you the period this time and I ask you to find the spring constant? Well, let me write down the formula for you. And take us back to I don't know, the second week of classes in this course, where we started to really do a lot of work with formulas. And I said if you have difficulty with the math, it's better to put the numbers in first. Somewhere along the way that changed. I think if you put the numbers in first here, you're making things more difficult. I think we should simplify this first. And if you're in Math 20 right now, you will understand that one way to simplify this is to square both sides, because that will eliminate the square root. So if I square this side of the equation and this side of the equation, I'm going to get t squared equals 4 pi squared. 2 squared is 4. When I square pi, I get pi squared. When I square the root m over k, this is what I get. The square of a square root is just the thing underneath the square root. If I multiply both sides by k, also known as cross multiply here, I get this. What am I after here? Am I after the period? No, I know the period. I guess I'm after the spring constant. So I can divide both sides by t squared and get 4 pi squared m over t squared. Was the period 0.46? Is that what I saw? 4.2? Thank you. So I'm going to take 4 times pi squared, don't forget to square the pi, times the mass of 0.5, divided by 0.42, which is the period, and don't forget to square that. So we're getting a spring constant of about 112 newtons per meter. What we're really getting today is practice using a new formula. That's what it boils down to. Tomorrow will be your opportunity to confirm that that formula works, because you'll be given a spring and a variety of masses and a stopwatch. Take a look at 3. What is the period of oscillation of a mass spring system that is oscillating with a particular amplitude and moving with a particular maximum speed? So how do we find the period? Well, we find the period using this. Correct? What is preventing us from finding the period using that formula? We don't know the mass. But we do know the maximum displacement. We do know the maximum displacement. And we do know the maximum speed. And the maximum speed corresponds to all kinetic energy. And the maximum displacement corresponds to all potential energy. So what we have to do, and I talked about this in yesterday's lesson with an example, is sometimes you have to use conservation of energy to find something before you can answer a question. 1/2 kx squared has to equal 1/2 mv squared, which means kx squared equals mv squared. Our goal is to determine this first. I hope you understand this blue thing I've highlighted here has no direct connection to the other blue thing. I should have used green, but you get the idea. That's the first thing we need to do. And then this will be the second thing we need to do. It's just a two-step question. So K 5.03 times the maximum displacement squared equals m, which we don't know, times the maximum speed squared. And you know, physics isn't for everybody, but ultimately you need to use math and you need to use physics. The physics is done here. It's just a matter now of putting the numbers into the formulas. The physics is setting up how to solve the problem. The math is getting the answer to the question. So let's all calculate that mass, 5.03 times 0.1225 squared, and I need to divide by 5.13 squared. I didn't check my units. Those are all standard units. Yep, they are now. So I get this for a mass. Anybody else get that for a mass? So it's a little bit more than 2 grams. It's a tiny little mass. But that's the mass. And now I can put that mass in here along with the, what was it, 5.03 newtons per meter. Boy, 5.03, 5.13 in this question, you get to be on your toes there. So 2 pi square root of that number divided by 5.03, about 0.15 seconds. You getting that number? Okay. That's it. That's this lesson. 3 quick examples. With regards to the pendulum lesson, so now you're going to turn forward a couple of pages till you get to the one on pendula. There's an extra thing that we want to talk about here, but it's so minor. We'll do it, but it's not a big deal. It's finding what's called a restoring force. What's really interesting here is the formula for the period of a pendulum is very close. It is identical in structure to the period of a mass on a spring. Think about this for a second. Would you agree that on a spring, the larger the mass, the larger the period? Okay. Would you agree on a pendulum? I haven't got this set up to do it, but if I want a longer period, I could get the string to be longer. So I'm going to write here what the formula is that we just learned for the period of a mass on a spring. That it's m over k, isn't it? That the bigger the mass, the bigger the period. That's why mass is on the top. The bigger the length, the bigger the period. I think you would also agree that with a mass on a spring, if the spring constant is quite small, the period will be quite big. I think you would also agree that if the gravitational field strength that the pendulum is in is very weak, the period is going to be longer as well. So there's a direct relationship between the period and the length, or the period and the mass, but there's an inverse relationship between the period in g and the period in k. It's an inverse square root relationship. It's a complicated one, but it's an inverse. So very, very similar structures. The difference here is that there is a restriction on when you're allowed to use this pendulum formula. And it's that you can only use it when the angle of deflection from the equilibrium position is less than about 15 degrees. The fact that I've highlighted the word than tells me I probably typed then in your handout. No? It is than? Okay, then I fixed it. So let's take a look at a couple of questions. What's the period and frequency of a 2.5 meter long pendulum? Where is this pendulum on Earth? We're not going to assume it's somewhere else because you don't have enough information. So the period will be 2 pi root 2.5 over 9.81. That's it. That's all we need to do. And then take the reciprocal to get the frequency. .2 seconds. Frequency is the reciprocal of the period, be about 0.33. Well, 0.32 hertz, 0.32 hertz. Again, I just took a different approach this semester. What I want us to do is just learn how to use the formulas today, and then we'll look at doing the lab work tomorrow. Pendulum on Earth has a period of 3 seconds. How long is the pendulum? Well, it's going to be pretty close to 2.5 meters, isn't it? So maybe we'll leave it. We're not going to get 2.5 meters, but it should be close. Just like the second question with the mass on a spring, I think what we should do first is square both sides so you can find L. When I square 2, I get 4. When I square pi, I get pi squared. When I square a square root, I get what's under the square root. Cross multiplying gives me gt squared equals 4 pi squared L, which means L will be equal to gt squared over 4 pi squared. We all know the value of G, right? 9.81. I would like you to run this through your calculator and get an answer. So I get 2.24 meters, rounded. Did anybody get an answer that's not that? Either nobody did or nobody wants to say they did. If you go 9.81 times 3 squared, which is 9, divided by 4 pi squared, why is that going to give you the wrong answer? Yeah. Right. So what this means is the calculator is going to take 9.81, it's going to multiply by 9, it's going to divide by 4, and then there's a multiplication sign in here, so it's going to multiply by pi squared. In order for you to get the right answer, so this is clearly not close to the 2.5 meters, you either have to do this, or what I typically do, which is to divide by 4 and divide by pi squared. So we're all okay with, and make sure your calculator registers that decimal. There we go. So make sure you know how to use your calculator properly. That's all. I think we have one final example here before we talk about the restoring force of a pendulum. A 50 centimeter long pendulum is swinging on the surface of a planet with a particular mass and a particular radius. The question is, what's the period of the pendulum? Okay. What do we need to find here? Well, we need to find the period, which is 2 pi root L over G, but we don't know G. We're getting near the end of the course. These are some things that you should be familiar with. That, if I want to find the acceleration due to gravity on an unknown planet, I use the formula for gravitational field strength. So we have to calculate G first by using the universal G, which is different than little g, times the mass of the planet over the radius of the planet squared. It's been a while, so you might have to look that up. Oh, not that long ago. We were doing satellite motion recently. Times the mass of the planet, 2.8 multiplied by 10 to the 22, divided by the radius squared, which is 4.3, multiplied by 10 to the 5 squared. I'll just step back and look at my entries, make sure they're right. Looks okay. We're pretty close to Earth, isn't it? If I use this as a multiple choice exam question, there would be one answer that would be the correct answer and another one that would be very close to the correct answer for the person who used 9.81. But they would be different. So this is G. Little g is 10.1. Meters per second squared, newtons per meter, whatever set of units you feel comfortable with. So now I can put that number into my formula, 2 pi multiplied by the square root of L, which was 0.5 meters. It was a 50 centimeter long pendulum, which is 0.5 meters, divided by G, so about 1.40 seconds.